I have a feeling this exercise was designed to give us an appreciation for the divergence theorem. We are to verify it for the vector field f of x, y, z equals x squared negative y, z on E, which is a solid cylinder, y squared plus z squared equals 9, x going from 0 to 2. Verifying the divergence theorem means that we are to show that the flux, that is the double integral over the surface S of f dot ds, is equal to the triple integral over E of the divergence of f dv. So we compute both of them separately and then show that we get the same result. Well, let's look at our solid. We have here a cylinder. X goes from 0 to 2. Radius of the cylinder is 3. For the flux, we have the surface integral over S of f dot ds. On our cylinder, we have three surfaces. One of them is the cylindrical wall. One of them is the back face of the cylinder. And one of them is the front face of the cylinder. Let's say the cylindrical wall is S1. The front face, where x equals 2, is going to be S2. And the back face, where x equals 0, we're going to say is S3. So the surface integral over S is going to be the sum of the surface integrals over S1, S2, and S3. Starting with S1, which is the cylindrical wall, since the cylinder has a fixed radius of 3, we don't need to use a variable to express that. We do have x going from 0 to 2, so we'd like to use a variable x. So we're going to set r as a function of x and theta. And we'll say that r is going to be x, 3 cosine of theta, 3 sine of theta, where x goes from 0 to 2, and theta goes from 0 to 2 pi. Now, we're computing f dot ds, so we need a couple of things. One of them is we need f expressed in terms of our parameterization. And then we also need ds, which is going to be a cross product of partial derivatives. F of r of x theta is going to be x squared. And then f is what? Negative y and then z. So it's x squared, negative 3 cosine of theta, 3 sine of theta. Rx cross r theta will be ijk, this determinant. Rx is going to be 1, 0, 0. R theta is going to be 0, negative 3 sine of theta, 3 cosine of theta. And you'll see that that cross product gives us 0, negative 3 cosine theta, negative 3 sine theta. But for any particular value of theta, that's going to point inward. So to fix that, we use r theta cross rx, which has the opposite sign. And so for the correct orientation, our normal vector is 0, 3 cosine theta, 3 sine theta. Now the surface integral over S1 of f dot ds is then going to be the double integral over, we'll figure out the region in just a minute, but the dot product is going to be x squared times 0, negative 3 cosine theta times 3 cosine theta, 3 sine theta plus 3 sine theta. So we have negative 9 cosine squared theta plus 9 sine squared theta dx d theta, and we had already seen that x goes from 0 to 2 and theta goes from 0 to 2 pi. Our integrand actually fits the form of the double angle formula for the cosine function, so we end up with the integral from 0 to 2 pi of the integral from 0 to 2 of negative 9 times the cosine of 2 theta dx d theta. Integrating with respect to x, evaluating from 0 to 2, and then integrating again is going to give us negative 9 times the sine of 2 theta evaluated from 0 to 2 pi for a result of 0. Moving on to our next surface, S2 is a vertical disk of radius 3 and an x value of 2. Because we have a disk, r is not a fixed radius, and so we can parameterize in terms of r and theta. The x component is 2 for the entire disk. Y we're going to say is r cosine of theta. Z is r times the sine of theta. And so that gives us our vector function r. And folks, we have a vertical vertically facing, a vertically oriented disk, and our normal vector should be outward facing, and so points in the direction of the positive x-axis. Therefore, n is equal to the vector 1, 0, 0. F of r theta is equal to, now f was x squared, so 2 squared is 4, negative y, so negative r cosine of theta, z, so r sine of theta. The surface integral over S2 of f dot ds is then equal to the surface integral over S2 of f dot n ds. That second ds is not a vector, but we're going to actually kind of weasel out of this. This is the surface integral over 2. F dot n, well, n is 1, 0, 0. F has an x or an I component of 4. So this turns out to be 4 ds as our integrand. We can rewrite this as 4 times the integral over S2 of ds, but that's simply the area of the disk. And so this is 4 times 9 pi, where 9 pi is the area of that disk of radius 3. And so our answer here for S2 is 36 pi. Back to our solid, S3 is the vertical disk that has x equals 0. R of r theta will then be 0, r cosine theta, r sine theta. Our normal vector is going to point in the backwards direction, so in the negative x direction, so negative 1, 0, 0. And f of r theta is going to equal 0, negative r cosine of theta, r sine of theta. As it turns out, this means that f dot n is equal to negative 1 times 0, and then everything else is also 0, so 0, which means that our surface integral over S3 of f dot ds is also equal to 0. Summing these together, we have the surface integral over s of f dot ds is equal to 0 for the cylindrical wall plus 36 pi for the vertical face at x equals 2 plus 0 for the vertical face at x equals 0. Our answer is then 36 pi. Now, just when we thought we were done, folks, remember we are verifying the divergence theorem. We've only done the surface integral here. We're now going to do the triple integral over the divergence of f dv. And I believe I misspoke a moment ago. It's the triple integral over e of the divergence of f dv. Now for this, let's remind ourselves of what f is. It's x squared negative yz, and of what the divergence of f is, which is del dot f. Remember, del is a vector that has partial derivatives that acts on the components of f. And so the result is not a vector. I just wrote a vector. The partial of x squared with respect to x is going to be 2x. The partial of negative y with respect to y is going to be minus 1. The partial of z with respect to z is plus 1. And so our divergence of f is equal to 2x. We then have the triple integral over e of 2x dv. Now remember, e is a cylinder, and 2x is our integrand. X goes from 0 to 2. I'm going to kind of weasel out of this one as well, because that inner integral, after it's computed, will then be integrated with respect to, say, y and z, or r and theta. But folks, after we integrate with respect to x and then evaluate, we have the double integral over d of 4 dA. Well, that's 4 times the integral over d of dA. That's 4 times the area of a circle of radius 3. So our answer is once again 36 pi. And again, we could have expressed dA in polar coordinates and done the whole thing, and we'd still end up with the same 36 pi. Now, I said at the beginning of this exercise that this will give us an appreciation for the divergence theorem. Even if we had to compute this integral, it would have gone a lot quicker than computing the 3 surface integrals that we started out with.